ARMA model, how to fit these models. That's known as Box-Jenkins analysis, right? Very popular in the 70s and 80s. We don't use it so much nowadays, okay? Now, the Wahl's decomposition theorem is saying, well, if something is weakly stationary, you can always write it in the ARMA form. And if you can write it in the ARMA form, then that makes life very easy for us, because we know how to estimate ARMA models using Box-Jenkins techniques. We look at the autocorrelation function, the partial autocorrelation function, that tells you what P is and what Q is. So you know what the process is. And if you know what the process is, then you can forecast the future and so on. Then you understand, right, how the dynamics of that process work. Okay? So all that is well and good. Okay, so if the process is weakly stationary, then life is simple. Life is easy, life is good, because we know we can express it as an ARMA model, and we know how to estimate those models. Okay? Now, the problem is that most economic variables are not stationary. Okay? So the world that we live in, it seems, is such that we can't really go very far with the ARMA kind of models. Most economic variables are non-stationary. Okay? And when variables are non-stationary, then the standard kind of econometric methods that we use for estimation, for hypothesis testing, for inference, they don't work. Okay? They don't work. So then we need to understand what non-stationarity is and how we can deal with it, okay, in practice. So we are going to look at it in more detail, but I'll just give you an overview and some understanding of that. Okay, so just to give you an overview, what does it mean? The difference between something being stationary and something being non-stationary. Now, if a process is non-stationary, it could be non-stationary in many different ways. Okay? Maybe the mean is not constant. Okay? Then it's non-stationary. But if that's the only thing, then it's close to being stationary except for the mean. Okay? Then if you can somehow adjust for the mean, you're back in the stationary world. Okay? So some kinds of non-stationarity, they are simple and they are easy to deal with. And if we account for those, we can make an adjustment in the data, we can go back to the stationary case, and life becomes simple and good again. Okay? But there is one kind of non-stationarity which is fundamental, okay, and which we cannot easily get rid of. Okay? And that kind of non-stationarity is called unit root non-stationarity. Okay, so I'll explain the difference with a simple AR model. So consider an autoregressive model of order 1. So this is the model that we have. Is this a stationary process? depends on theta. Yeah, but if I don't tell you anything about theta, can we say whether this is stationary or non-stationary? No. Okay? So the value of theta is important in determining whether this process is stationary or non-stationary. Let us see why that is the case. Now, this yt minus 1, I can replace it with theta yt minus 2 plus epsilon t minus 1. Right? This equation holds for all t. This is notation for all. So this equation holds for all t. So this, in particular, yt minus 1, I can replace it with this. And then I simplify this. So I have this. Now, let me do that one more time. So if I do this kind of backward recursion once more, then what do I get? Right? So I could keep on going backwards in time until eventually I have theta to the power of t y0. Y0 is like the starting value of the process. So we assume the process yt has some constant starting value. Okay? And then the other things are just the other things are just this moving average component. So now my interest is in understanding whether this process is stationary or not. Right? So now if I compute the expected value, what do I get? Well, epsilon 1, epsilon 2, up to epsilon t, their mean values are 0, white noise. So what am I left with? Okay. Well, this doesn't look like it's constant, right? So it seems to depend on the initial value, y0, but notice that as t becomes larger and larger, this dependence on the initial value will become smaller and smaller, provided theta is less than 1. Okay? If theta is less than 1, as t becomes larger and larger, the expected value is going to converge to 0. If theta is smaller than 1 in absolute value. Okay? So if I want the mean to be a constant, then theta needs to be smaller than 1 in absolute value. Okay? Second, let us look at the variance of this process yt. What's the variance going to be? So I have this. What's the variance of this going to be? Well, what's the variance of the first term? Well, the first term, y0, we are assuming is constant, so variance should be 0. Variance of a constant should be 0. Okay? And then what about these? Okay, so let's split this up. So variance of each individual term plus what else should we have? We should have all the covariance terms, right? Now here we have a white noise. This is a constant. All the covariance terms are going to be 0, right? White noise, they are uncorrelated with each other by construction. So we have some covariance terms which are all 0. So I'm not going to write this whole thing out. So what do we get here? Now this is a constant, so this variance is 0. Variance of epsilon t, sigma square, theta epsilon t minus 1, variance is going to be theta square sigma square theta to the 2t minus 1 sigma square. So that is the variance of yt. So we can write this as 1 plus theta square up to theta to the 2 times t minus 1. And that's going to be so suppose A is equal to theta square. So I have a geometric series over here, 1 plus a plus up to a to the t minus 1. I can write this as 1 minus a to the power of t divided by 1 minus a. So this is basically sigma square so that's variance of yt. Again, this depends on time. So if I want this AR process to be stationary, what must happen? So again, if theta is smaller than 1 in absolute value, then theta square times t, theta to the power 2t will go to 0 as t goes to infinity. So again, this will converge to sigma square over 1 minus theta square if theta is smaller than 1 in absolute value. Okay, so we have seen that for an AR process to be stationary, right, theta needs to be smaller than 1 in absolute value. Okay, so it can be shown so this process is stationary if and only if theta is smaller than 1 in absolute value. Okay, so then you have a stationary AR1 process. Okay, so this would be nice to have, but for economic variables, especially in macro and international finance, it turns out that this description doesn't work for many variables. Instead, what we have is this. And that means theta is equal to 1. Then we say that this time series has a unit root and it is non-stationary. Okay? So there are many kinds of non-stationarity, but unit root non-stationarity is the most important kind. The most important kind of non-stationarity. Okay, so let's look at an example to illustrate what this means. Okay, so most famous example of unit root, which economic variable has unit root? Stock prices. Okay, so stock prices are, if you try to estimate a model that describes stock price movements, then unit root model seems to be a very good choice for explaining stock price movements. And what does it really say? So this is simple unit root model, and so you can rewrite it as follows. So this is the model in levels, and you can write it as a first difference. So the change in yt is epsilon t. What does that tell us? This is the random walk model. So the random walk model is saying that the change in yt is purely random. It is a white noise. It is unpredictable, unforecastable. Okay? So if someone asks you, what is your best forecast of the Hang Seng Index tomorrow? What should your answer be? No, don't pick a random number. Today's price. Okay? You're saying that the change from today to tomorrow is unpredictable. Okay, it's a white noise. So the expected value of this white noise is 0. So that is your best forecast for the change between today and tomorrow. Okay? So we're saying stock prices are essentially unforecastable, okay, unpredictable. And so this is the random walk model of stock prices, and this is implied by the efficient market hypothesis. Okay, so the efficient market hypothesis formulated by Eugene Fama, he got a Nobel Prize in economics for this, right? And in this, he's basically saying that the stock market is efficient. And what does that mean? It means that the stock market incorporates all the available and relevant information into the stock price today. Okay? Anything that is known about that stock, it should be reflected in today's stock price if the market is efficient. And so if everything has been already reflected in today's price, then the price tomorrow should be the same as today's price plus some unforecastable random error. Okay? So there is some news which will arrive tomorrow, and based on all information today, we cannot predict what this news is. It is news by definition. We don't know what it is today. It's going to be something new tomorrow. Okay? Other than that, everything that is known today is already incorporated in the stock price. Okay? So if markets are efficient, then they should follow a random walk. Stock prices should follow a random walk. And so this is an example of a unit root. Now, when Fama estimated models of the stock price, he found evidence of this efficient market hypothesis, and he saw that unit root model or random walk model explained stock price behavior better than some other ARMA models or other kinds of models. So he concluded that efficient market hypothesis tends to hold in the data, and so stock market is efficient. Okay? But since then, a lot of research has been done which shows that the stock market is not 100% efficient. Okay? Maybe 80 to 90%. But there are deviations from this random walk theory which make the market less than efficient. Okay? So what would be some examples of deviations where the market fails to be efficient. It fails to be efficient means that there should be some element of predictability. Right? Efficient market hypothesis is saying, well, there is no predictability. The change between today and tomorrow, that's a white noise, it's pure noise, unknowable today. Okay? But certain kinds of changes are predictable. Okay? So maybe just one example of a change. So suppose that there is going to be an earnings announcement at time 0. Okay, this clearly is an important thing for a stock. Right? If the earnings are going to be announced, that is big news, right? And that could have a huge impact on the stock. So suppose that the stock market is predicting or expecting that the earnings will be $2 per share. The earnings number is going to be announced. So this is what is expected. Now suppose the actual earnings turns out to be $3 per share. Okay? So when the earnings is announced, what should happen to the stock price? It should increase, it should go up, right? Earnings are higher than expected. That is good news, right? Good news. So there is good news. So suppose this is the stock price before. Okay. So it's fluctuating randomly, and then news comes out and t equals 0, and this is good news, much better than what the market was expecting. So the stock price will jump to a higher level, and then it should kind of fluctuate here until there is another big piece of news. Okay? So the efficient market hypothesis tells us that when there is news, the stock will immediately jump to its new equilibrium level, and it will stay there until there is another news that changes the stock again. Okay? Now, in reality, is that what we observe when there is an earnings announcement? No. What do we observe? Okay? Yeah. So what we observe is that it doesn't fully increase. Rather, it will jump, and then over the following days, it gradually drifts upwards towards the new equilibrium level. Okay? So this is called the post-announcement announcement earnings drift. Post earnings announcement drift. Post earnings announcement drift. Okay. So what does this tell you? If you want to be rich, what should you do? Watch the news? That's not enough. That's necessary but not sufficient, right? How can you take advantage of this predictability? How can you take advantage of this predictability to earn abnormal returns in the stock market? What kind? Sorry? All the labels? Options or futures or something like that? Okay, so here's the thing. When would you buy them? Before the announcement. Before the announcement, you don't know whether earnings will be good or bad, right? So unless you have some specific, if you have some insider information, the CEO is a good friend, he tells you, well, something nice is going to happen, that's a different story, okay? Or you are Warren Buffett, you really understand the business so well that you are able to see something which other analysts in the market cannot see, okay? But we rule out these cases, right? Warren Buffett is unique and the CEO is not our friend, so we don't have inside information, okay? Then the beauty of this is that you don't need inside information. This kind of grid, it is observable. So when there is good news, earnings are significantly better than expected, then you wait for the news, right? You observe the news and you buy over here on the first day, right? As soon as the news is announced, the stock price goes up. Suppose it's up by 5%, 7%. Still, you know that in the next few days, it's going to complete its adjustment. The adjustment is not completed on day one. So even after the news comes out, the stock is already up by 5%, 7%. It's not too late to buy. Okay? So you buy after the news is revealed and the stock price is up. You wait for a few days until the adjustment is complete, and then you sell. Okay? You're done. That's all you need to do. You don't need any inside information. You don't need to predict the earnings. All that is very difficult. This is something simple and easy that you can do at your own risk. Okay? You can play with this. It works, not every time, but it works surprisingly well. Okay. So if the market was efficient, then so if the market was efficient, it would immediately jump to the new equilibrium and stay there. But what we see in the data is that it jumps up partially and then drifts upward, this drift is a predictable change, and therefore this violates the efficient markets hypothesis. Okay, I think we should take a break here. So get some drinks, and then, so about 15 minutes.
这个你可以调这个的，所有键你都可以调，这边还有一键，所有键我知道，你可以调那个，我一般调那个，到时间回归桌面。这个我们这个坏的。这有没有坏呀？你不要跟我炫了，我上次就完了。这些都是啥？那个的后台可以带上的一个意思。我应该用1年，2个用1年。我要去打一个东西。
或者是，毕竟还没到，周老师一直打。我去不是打那个 topics，
你就感觉在用这个，我就选这个吃的时候，不过它是直接在上面滑来切换这个。这是什么？核桃还是壁咚咚？不知道。我不知道谁拿到的。上这个点头，因为有它是有芝士了吗？这个给大家说。我发现芝士好贵啊！我昨天买了一小袋子，80块钱。马苏里来了，不是马苏里来了。
去打印了吧？
他这个比我还要晚，就是什么？我昨天早上去。那你昨晚？